Okay, hi everyone. Good morning. What we're doing today is we're going to work on horizontal asymptotes. Yay! That means we learned how to graph vertical asymptotes last time, which help us break up that rational function. So we can look up when we divide by 0, that's a no-no for us in essence. And what we can do from there is draw up the guidelines to help us figure out what this graph should look like. All right, so let's go ahead and look at our rules that we've covered before. So we talked about previously vertical asymptotes. And that's the idea is when I'm dividing by 0, and we'll use our example like before, we'll use x minus 2 this time. So we have our fraction, and our rules for fractions is that you cannot divide by 0. We do not want this to be 1 over 0, because that's what we call undefined. And we make a big deal is that if you are dividing by 0, if x equals to 2, we are screwed. 1 over 2 minus 2 is 1 over 0, and then we're dead in the water. And that's actually a hint that these are characteristics of this graph. Like your parents don't tell you for the most part where you could play. They just say don't play, like don't cross the street, right? Don't go into the neighbor's yard. Don't go past that tree. Don't go on my side of the room. Don't come in my room, all this stuff. So the idea is where should we not go? We're not allowed to be at -2. So at 1, 2, we draw a dotted line, and this is to remind us this is a vertical asymptote, VA, and that we are not going to touch that line. Now today we're going to draw this second boundary. It's called a horizontal asymptote, and our horizontal asymptote automatically, I can tell you from my experience, is that it's going to be right here, horizontal asymptote, HA. And by knowing these two ideas, that we can trap our graph, we're going to trap it in these corners here. As you can see, as we head toward the vertical asymptote, the graph doesn't cross through, it doesn't break through, it goes to infinity. It's going to get dragged up. It's almost like it's caught up in a tornado, right? A tornado. Whoa, look, it's being caught up in the tornado. And going the other way, as I head towards 0, we're going to get we're not going to cross through it. We're going to get caught up in this whirlpool. Whoops. Yeah, that's true. That's a whirlpool. Whirlpool is more like the other way, right? Okay, whatever. So today we're going to work on this horizontal asymptote idea, and it's going to be pretty easy. We have 3 rules to follow, and only 3. And your problem's going to fall into one of these 3 criteria. So let's go ahead and go through these 3 criteria. So rules for horizontal asymptotes. Now, before we get started with the rules, we want to say what do these problems look like? And they look like a function with a numerator and a denominator, right? Why do we call them rationals? Is because they are fractions. These are rationals, and these are, essentially fractions. Well, the fraction has to look like a polynomial for us. And that means it's not going to have an ln in it. It's not going to have some weird e to the x. This is just going to be some type of problem that says, here's my easy example. It would be like x cubed plus 2x squared plus x plus 1 over 4x cubed plus 2x squared minus x plus 1. Something like that, okay? It's going to be a polynomial over polynomial, and these rules work for these. We've seen polynomials before. Now we're going to have a polynomial on top and on bottom. Now the generic way of writing this, now you might find this a little confusing, but this is generic. We have some number in the front with an exponent to an nth power. Maybe that's 3, 4, 5, my biggest exponent. We'll call this a1, x to the n. Our next term is going to be a2. Our second term, x to the drop n exponent, n minus 1. So if it's 3, n is 3, n minus 1 will be 2. It's my next following value. Plus a3, x to the n minus 2. And this is going to go on for blah, 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 blah. A4, A5, A6. Exponents will go n minus 3, n minus 4, n minus, just dropping all the way down. On the bottom, we're going to give ourselves a different value, b, because a and b don't have to be the same. b1, x to the m, we use m. Why? Because n on top doesn't mean it's going to be n on the bottom. They could be different variables, so we'll just call that a different variable, m, plus b2, x to the m minus 1. Oops, sorry, let me make that look a little better. And then we're going to go to b3, x to the m minus 2. And then this goes on forever as long as you want. As many terms as you need, I'll give you those terms. Okay. So this looks very complicated right here. But all it's saying is I have a number in front with an exponent, number in front with an exponent, a number in front with an exponent. And these exponents drop, 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 drop. Okay. That's all this is saying, a generic way of looking at it. And we are actually only going to focus on the front pattern right here, because these are the biggest bullies. And this will guide our graph. This will guide our graph. Okay, so before I get to this, I want to make sure you guys can understand this part. For this problem here, what is our a value and what's our n value? Okay, what's our a value and what's our n value for this problem here? What is our b value and what's our m value? For our problem here, I just want you guys to figure out if you guys can catch what these numbers would represent. What's the a value, a1? What's the number in front? And then what's the n value on top? So my first example, the front would have been an invisible 1 with the exponent of 3. Okay. For the b1, that front value would be 4 with the exponent of 3. We're just making sure you guys can catch what the exponents are going to be. Okay. Now, that's all you have to pay attention to. Now, the biggest thing that we're going to use right now is this exponent value. Are the exponents going to be the same? Is one going to be bigger than the other? And which one will be the bigger one? So here's our first rule. So rule number 1. And here's the rule. The rule is if m is bigger than n. Okay, if m is bigger than n. Horizontal asymptote. Asymptote. Y is equal to 0. First rule, we have only three rules when it comes to horizontal asymptotes. You look at the exponent, and if the exponent is bigger than the denominator, we have a horizontal asymptote at 0. Now, why is this? Why am I saying that the bigger one on the bottom has to be true versus the top? An example of this is, let's take a look at this problem. Here's my example. Y is equal to x to the 5th plus 6x over x to the 6th plus 4. Okay, here's a problem. Now, which exponent is bigger? Which exponent is bigger? I would say, looking at m and n, just to make sure, n is 5 and m is 6. If the bottom one is a bigger bully, take a look here. If the bottom is a bigger bully, we end up dividing by a bigger exponent. Here's what I'm going to say right now. Our horizontal asymptote, y is equal to 0. Okay, so here's our rule, is that if the bottom exponent is larger, our horizontal asymptote is automatically going to be 0. That means I can for sure tell you that no matter what this graph looks like, our graph is going to be drawn toward the horizontal asymptote. Eventually the graph is going to go to 0, and the graph will go to 0 eventually. Okay, so we know what the end behavior of this graph is. And we talked about before, for regular polynomials, like x cubed, x squared, we could talk about how would this graph exit the graph. Now, I want to show you something that I have on Desmos real quick. Now, I do something on Desmos. Oh, darn it, disappeared. But what if I give you guys, here's our problem. I'm going to make this up right now. I'm going to give myself an exponent. I'm going to call this exponent the letter a. Oh, sorry, we're going to use the letter m. And then we're going to give ourselves an exponent up here, x with the exponent of n. Add slider. I'm going to do a couple of tricks to this. I want to make sure this is starting at 0. 0. And then we can go in steps of 1, 1. Okay. And we'll say this is 6 and 6. Okay. Okay, so first thing I want you guys to notice is taking a look here, is that if the exponents were, which one's bigger? Which one's bigger? Which exponent is bigger, n or m? N representing the top exponent, m representing the bottom exponent. And if m was bigger, take a look here, the graph, no matter what, as long as m is bigger than the top value, our graph eventually ends up at 0. And let me show you what I mean by that. Is that the horizontal asymptote here is 0. The graph will eventually become 0. Well, what if the exponent on top was bigger? If they are bigger, take a look. If the top is bigger, does this graph get stuck at 0? Nope. As long as it's bigger, no matter what, we do not have a horizontal asymptote. But once we become less than it, take a look, we are now stuck back at 0. And this is a rule we want to make sure we can capture and understand, is that if my exponent on the bottom is bigger, no matter what that number is, we are always going to get stuck to 0. Okay. What if the exponents were exactly the same now? Now, I want you guys to notice, in this case, the horizontal asymptote is stuck at, I want you guys to see if you guys can make a guess here. What is the graph getting stuck at? And hopefully you can see it. The number is 1 here. Why is it 1? Let's go ahead and talk about why it's 1 now. So rule number 2, if the exponents are exactly the same. What if the exponents are exactly the same? If this was x cubed, oh, let me actually finish the rule. If the exponents are exactly the same, the horizontal asymptote, y is equal to a1 over b1. Now, where does a1 over b1 come from? Let's go back and look at our previous problem up here. a1 and b1 are the front coefficients of that highest power. It's just the front of the equation, of course, in order, highest power. That a1 and b1 are those front coefficients. So I'm going to give you a couple of them here. If I say x cubed over x cubed minus 1, these are pretty darn close, aren't they? Pretty darn close. But what is the front coefficient? An invisible 1 and invisible 1. So what is the horizontal asymptote? Y is equal to 1 over 1, which is equal to 1. Now, why would this be? And is there some type of magical rule here? No, these are what I call shortcut rules. They're patterns that we can resolve by doing these enough times. Hey, there's a pattern here. The pattern is that if we have the same exponent, it's almost like two runners that run at the same speed. If two runners run at the same speed, do they really get far from each other? Have you ever ran with a friend who runs about the same speed as you? You guys are always, near each other. But have you ever ran with someone that's way faster than you? They leave you behind. And that's what I'm looking at here. X cubed are about the same speed. So let's plug in some numbers. As x gets bigger, let's say if we plug in 10, x equals to 10. Well, this would be 1,000 over 1,001. Isn't that approximately 1? Okay. What about if I plug in 100? X equals to 100. This would be 10,000. Oh no, that's 100,000. Oh wait, let's see. 1, 2, 3, 4, 5. That's a million actually. A million over 1,000,001. Okay. What's a million divided by 1,000,001? Isn't that even closer to 1? The idea is if they have the same exponent, the numbers never were going to get too far from each other. And as x goes to infinity, as the graph goes out to the right and out to the left, we become our horizontal asymptote, whatever that value would be. Now, what if the numbers changed? If I said y is equal to 3x squared over 5x squared plus 1, okay? Again, this could be filled with a bunch of other stuff. We're keeping it simple just so you guys can see the illustration here. The biggest bully is going to be 3x squared and 5x squared. Now, if I plug in 10, here let's plug in 10. X is 10. This would be 300 divided by 501. What is 300 divided by 501? That's pretty darn close to 3 over 5. What if we say x is 100 now? That's going to be 3, 1, 2, 3, 4 over 5, 1, 2, 3, 4, and 1. Isn't this even closer to 3 over 5? So as x gets bigger, as we again flee the graph, and the numbers get larger, the fraction becomes closer to our horizontal asymptote. Now looking here, what's the exponent? So the exponents are 2 and 2. That means they're exactly the same. Our horizontal asymptote rule says we're just going to copy the front values. Here's a tricky one that they like giving. Y is equal to, let's say, 4x squared plus 3 over 1 minus 3x squared. Okay? I want you to take a look at this problem and ask yourself, what is the biggest exponent for these problems? Is the top exponent bigger, the bottom exponent bigger, or are they exactly the same? Do they follow rule 1 or rule 2? And looking at the exponents, squared and squared, these are actually the same problem. Sorry, the same exponent. If you want to rewrite this, you can, but I find it's just a waste of time if you can already spot the largest exponent. If I rewrite it, it becomes really obvious that these exponents here are the same weight. They're the same weight. So what's my horizontal asymptote? Horizontal asymptote is just 4 divided by -3. Y is equal to, my horizontal asymptote is equal to 4 over -3, or -1/3. Or you know what, you can just leave it as -4 over 3. But I want to make sure you guys can see that because I'm going to graph this right now. Now, you could break out decimals for every one of these problems. And I'm going to tell you, it's a waste of your time. It is a waste of your time. Because we can graph this so much faster than you can type it in the decimals, especially if you don't have a calculator, if you don't have a keyboard. So I'm going to write 4x squared, squared, plus 3. And on the bottom, we're going to say parentheses divide by 1 minus 3x squared, right? So, let's see if I copied it right. Okay, so the question is, what's the horizontal asymptote? What will this graph eventually trend toward? And let's take a look here. The graph would eventually become, I'm not sure if you can see it. Let me go ahead and pick a point. This graph here, that's my horizontal asymptote. This is eventually is the direction of this graph. Now take a look at what the answer is. Really close to the middle of the graph, we can't see the horizontal asymptote. But as the graph gets farther and farther away from the center, as we approach infinity, let's look on the right side. I want you guys to look at this number, -2, -5, -4, -3, -3.6, -3.3, -3.34, -3.33, -3. Which is approximately what we said, -1.33. And that's my horizontal asymptote. And that's where the graph gets stuck on. And this is the graph, the direction the graph will start trending. So I can tell you what the horizontal asymptote is by just simply looking at our rule. Is the top exponent bigger? If it's bigger, it's going to go to 0. If the bottom exponent and the top exponent are exactly the same, right? That means we just copy the front coefficients, meaning from our largest exponent. And that's going to be x squared and x squared here. Don't forget the negative. Now, I'm going to show you a trick here. Now, what if that 2 became a 3? Now who's bigger? The top or the bottom? Now the bottom exponent is bigger, and you take a look, the graph tends towards 0. See, the graph tends towards 0. That's 0, and that's 0. Now, what if I made the top exponent bigger? What if I call that all of a sudden 4? Does that look like it has a horizontal asymptote anymore? And the answer is no. It does, though, have a slanted asymptote. Take a look here. That's slanted, isn't it? And what happens is that as a graph gets closer to infinity, it doesn't go to a horizontal point, it actually follows a line. And that's what we call a slanted asymptote. And we'll talk about that next time, but we will throw that as a stipulation for our rule. So here we go. Let's go talk about our third rule now. The third rule is that if I have the top exponent being bigger now. So here's rule number 3. If m is less than n, meaning this is the top and bottom, if the top exponent is bigger, we have no horizontal asymptote. And this is where the rule no longer becomes easy. So hopefully our bottom exponent will be bigger, or they'll at least be the same. Now, no horizontal asymptote, that is the reason why, because what happens is this graph will shoot off, maybe it might shoot off to infinity, but it's no longer stuck to one boundary. We can't tame this horse anymore. It's gone mad. It's going to shoot off to infinity, and we can almost guarantee you that it'll shoot off to infinity in some way, shape, or form. No horizontal asymptote. Now, does this follow a rule, the rules that we've talked about before? You know what? If I write x squared over 1, hey, does this follow our rule? Isn't the top exponent bigger than the bottom? And for this graph, there is no horizontal asymptote. It shoots off to infinity. What if I wrote x squared divided by x squared? Well, doesn't this divide out to be 1? What if I edge it over? What if I say x squared over x squared plus 1? Now they don't cancel out, do they? But if x was big enough, like we mentioned before, this would look like 1. Wouldn't it? What if I wrote 3x squared over 2x squared plus 1? Sure, they don't cancel out. But if x was big enough, as I mentioned before, if x was like, say, 100, this would be 30,000 divided by 20,001. Isn't that kind of close to 3 over 2? And the idea is as x gets bigger, we are going to get trapped at 3 over 2. And the rule simply just says, if the exponents are the same, go ahead and just copy the front coefficients, and that's our horizontal asymptote. And if they're not, don't worry about it. Now on your homework, you're going to see problems like this. And let's go ahead and log in here. Sorry about that. I know today we do have a short day. Whoops, I shouldn't be showing that. So for your homework, it's pretty darn easy, because if you can catch these 3 rules, is the top exponent bigger, is the bottom exponent, are they the same, what is the horizontal asymptote, we can see what the behavior is. So for each function, determine the long run behavior. In this case, our end behavior, our horizontal asymptote. So look at my problem number 1. Is the top exponent bigger or the bottom exponent bigger? Are they exactly the same? Hopefully you notice that they're exactly the same. So we have a horizontal asymptote, and since the front is x squared, invisible 1's in front, we are automatically at 1. Look at the second problem. Is the top bigger or the bottom bigger? You can see that the bottom is bigger, we're going to be at 0. And the third one, is the top bigger or the bottom bigger? If the top is bigger, we have no horizontal asymptote, no horizontal asymptote. Now you're going to be asked to do this question 4 times, even though they look exactly the same. 4 times. And hopefully by the 4th time, you've caught on. If the top is bigger, the bottom is bigger, or they're exactly the same. You can do this like 5 times, never mind. Yeah, like 5 times. Now, this question here is, hey, now that we get the pattern, hopefully get the pattern, what's the horizontal asymptote? Looking at this problem, look at my largest exponent. You might think it's a 5x, right? Nope, they rewrote it. My largest exponent is the x cubed. So if we have the same exponent, we just copy the front coefficient. How fast is this problem? It's faster for me to talk about it than write it. Okay, if you want to rewrite the problem, sure. Negative 4x cubed minus 5x minus 1 and 5x cubed plus 4x squared minus 2. I can bet you that this graph will eventually look like negative 4 over 5. This story is almost like if you want to know what your girlfriend will look like when she gets older, look at your girlfriend's mom. Same thing. Want to figure out what your boyfriend's gonna look like when he's older. Okay, I mean, you guys aren't gonna marry them right now, but let's say, look at their dad. Right? Oftentimes, your parents look like your grandparents as they age, and that's what happens. As we age, we'll look like our older selves, our parents. Look at the second problem here. Same idea. Look at the largest exponent. This is 2 over negative 5. Automatically, I can see that the horizontal asymptote is going to be 2 over negative 5. What about problems like number 10, where they don't write it out for you? So what you're going to do is you are going to multiply out. But please take this hint. When we're looking for horizontal asymptotes, I'm only looking at that front coefficient. So just multiply the fronts together. That'll be 7 times x times 2x. That will be the front value. On the bottom, it won't be x here. Remember, we're only multiplying our exponents here. It's really just x and negative x and 5x. So what will those front coefficients be? This will be 14x squared and negative 5x squared. Take a look. They have the same exponent, right? They have the same exponent. And what does the rule say when they have the same exponent? We just copy the front value here. The same thing happens for our next problem over here. What's the original polynomial? Remember, this rule only works when it's written in polynomial form, meaning you have to multiply it out. Now, I don't want you guys to multiply everything out because I don't need the whole problem multiplied out. We just need to see what the largest exponent is going to be. So the largest exponent here is we're going to take the 6. You have to take the 6 because 6 is on top, is 6 over 1. 6 times x times 8x. That'll give me my largest exponent. On the bottom, it's going to be negative 1 times 6. So negative 1x times 6x. This is going to be 48x squared over negative 6x. You can reduce that because 48 does divide into 6. That's going to be 8 times negative 8 over 1 or negative 8. So that's my horizontal asymptote. Automatically, you just take the front. Oh, sorry, that was going to be squared. I didn't write the squared. Because they have the same exponent, we can automatically say it's just a front. Okay, easy peasy. Now looking here, we're going to follow the rules. What's the Y-intercept? Now, how do I find the Y-intercept? Please, if you guys remember, how to find the Y-intercept of a graph. This is straight from Algebra 1. You plug in x is equal to 0. So make x equal to 0. Now, here's the cool part when it's written this way. 0, 0, 0, 0. What's the only number left? Just take those back numbers and divide them. Because if I plug in zeros, we're only left with those constants at the end. That's going to be 20 divided by 5. 20 divided by 5 is 4. That's the Y-intercept. What's the X-intercept? Now the X-intercept is a little harder. It's when the top goes to 0. So this is a part of the rule that we kind of talked about in our last graph when it came to polynomials. When does a graph, what are the roots? What are the roots? And that's when the when y is equal to 0. So when we're looking for when y is equal to 0, we have to solve for the top going to 0. Okay, so you're going to take 3x squared plus 19x plus 20, and you're going to try factoring it. See if this is factorable. Now, this goes back to your factoring skills. Now, I can tell this is factorable because whenever I see a factoring problem, I automatically try to factor it. And I'm thinking, what numbers make up 3? 3 and 1. And probably 20 is going to be 4 and 5. So can you multiply this in such a way that you add up to 19? I want you guys to take these numbers, 3 and 1 times 4 and 5. And is there any combination that you could come up with when you're multiplying that adds up to 19? 3 times 4 or 3 times 5? You pick one. Well, 3 times 5 is 15. 1 times 4 is 4. And don't they add up to 19? We found one that works. So 3x, x, we said 3 times 5, and we need to put the 4 someplace. Plus, plus. What are the zeros here? If I want to make this go to 0, 3x plus 4 is equal to 0. Hopefully you can do that in your head. Minus the 4, divide the 3. X is negative 4 over 3. On the right, x plus 5 is equal to 0. Minus 5 to both sides. X equals to negative 5. We have our zeros. Those are the x-intercepts. Negative 4 over 3 and negative 5. What are the vertical asymptotes? We talked about vertical asymptotes in our last class. That's when the denominator equals to 0. So you'll be able to factor these problems. Hey, what are the factors here? 3, 1, 5, and 1. Can you think of a combination that makes them add up to 8 in the middle? 3x, x. Well, isn't 3 times 1 and 5 times 1? 3 plus 5 is 8. Yep, 3 times 1 and 5 on the other side. Plus, plus. The vertical asymptotes are when the denominator goes to 0. The denominator goes to 0 at negative 1, and 3x plus 5 is equal to 0. Move the 5, move the 3, negative 5 over 3. Negative 5 over 3, negative 1. So this is a skill that we worked on before. When does the denominator go to 0? And the last one, which turns out, which is our newest lesson, is the easiest one of these to calculate. Take a look at the exponent. The largest exponent is 2, so they are the same. That's rule number 2. If they're the same, we just copy the front. 3 divided by 3 is 1. Oh my goodness. The horizontal asymptote, the last one we learned, was actually the easiest one. X-intercepts, factor the top. Vertical asymptotes, factor the bottom. Y-intercept, the first one, plug in 0. All these require some work, but the easiest one turns out to be the last one we learned, horizontal asymptotes. Which of the 3 rules do we use? All right, that's it. Thank you.